Machine learning can be tricky because there's so many options available and there are a lot of training materials, and what I really want is just something that can get me started really quick. Because if I have a working example to start from, I'll be able to take that, iterate it on it, and overall I feel like I will learn a lot faster in that case. Obviously what we could do is we could walk through tutorials and examples and documentation, which is helpful to get like a general gist. But for me, when I'm learning something, I want to be able to have that deep understanding that comes when I actually get hands-on experience. While you're actually watching this video, this isn't the same thing as hands-on experience, but at least we'll be able to walk through a code example that's fairly straightforward. I mean, I would like it to be even more straightforward. However, there are just some patterns that we should be aware of when we're walking through AI models. A really great use case for AI today is being able to take organic information input as like text or audio or imagery or video, and then being able to provide some output or work based on that input. Generative AI is actually really exciting because it provides a pretty general purpose use case. However, it tends to be slow and quite expensive. We don't need that. If we want to be able to achieve very specific goals, we don't need to worry about prompts. What is that called? Like when you're prompting the AI, but then you're like tuning your prompt to get it to do exactly what you want it to do. You give it some examples, the number of shots. Well, you don't have to do that if you're training your own model, and also if you're training your own model on a very specific task, it'll perform really well, and it doesn't take a lot of energy or time to train it. All right, we're gonna walk through some of the code that we see typically in most common machine learning models. What we wanna do is create a quick script, a Python script that will input data, it'll consume it, it will prepare it for an AI model to be trained on, and then we can use that model to submit new work that it's never seen before, and it will give us answers. So we're gonna walk through some of that code right now, and we'll try to do it line by line and give as much detail as possible. My recommendation is starting with Keras, because that's one of the easiest AI model frameworks that works pretty well, actually really well. It uses all the performance needs that you can require. Also, it's the easiest. I would say it's the easiest. We've used TensorFlow directly, we've used PyTorch, scikit-learn, and Keras sits like nicely on top and is able to access the power and capabilities of other lower level machine learning models and their frameworks. Keras is a great place to start. And here we have NumPy, which is, it's a library that's written in C that you can use Python with to be able to interact with arrays and numbers really quickly and easily. So it gives you a lot of shorthand capabilities with operators and implemented methods that you can call upon. It's like a nice utility class dealing with matrices, which is the whole point. That's all what AI is they're matrices. So we're going to give ourselves some quick access here to the sequential model in Keras, which allows you to define a model and then append layers based on your needs for the AI model. And it will step through each layer and perform the tasks that you've stacked on it. And these are the layers that we're going to be using in the model, in the sequential model. The dense layer is just a full matrix. It's just a straight up matrix. And you can define the dimensions of that matrix. And these are the weights or the parameters, right, that we want to keep. These are the important things. And so what we're going to do is we're going to take that matrix and we're going to train it using stochastic gradient descent. And this line right here is only used at training time. We do not need this during runtime or inference time. After we've trained it, this layer, this optimizer, we don't need it anymore, because it's only used for training purposes. SGD, or stochastic gradient descent, is just the randomization of its input training data. So here, I'll jump down here real quick. Here's all of our training data. We've got sentences, and then we've got, these are our features, right? So it's a bunch of text. And then our labels are if it's got a negative aspect to it, like a light touch negative aspect. So we've got some answers like yes is negative, and right, 1 will indicate negative and 0 indicates non-negative. And with SGD, or stochastic gradient descent, what's going to happen is the model will train based on random selection of sentences, rather than going through each of those sentences sequentially one by one, right, where the AI will train on these sequentially one by one. Instead of doing that, it's going to train on this sentence first, and then this one, and it's going to go over here to that one, and then this one over here, and it will just randomly distribute them. It'll still capture all of them that you throw into it, but it will always shuffle. It's like a shuffle mode. We're doing a quick code walkthrough of a nice example of machine learning model, right? How do we make the computer, how do we train the computer to do something? Well, we use machine learning to do that. And the thing that we're talking about right now is hyperparameters, and that basically describes what the model looks like, the shape of it, expected input data, tokenization and embedding. There's all these strategies, because basically at the end of the day, you mostly have just a series of matrices stacked onto each other, and then the hyperparameters are defining what are the shapes of those matrices and then how we interact with them. Because that's really all it is. It's just matrices. One of the hyperparameters here in this case is what our alphabet looks like, or what our tokens are going to be. As we have input data of a bunch of sentences here, we want to figure out how we're going to tokenize that and then embed it to find general meanings based on the position of each characters, like the words and other things. So that way we can define, the computer can see, it can find patterns. And if it can see patterns across a nice array of a gradient, it's going to be able to better understand how to provide our answers. The answer we're looking for is whether a sentence has a negative aspect to it or not. So we've already got some training data here where it has a bunch of features and labels. Our features are the input sentences, and the label is if it has a negative aspect to it. So in our example here, we've defined an alphabet that is all lowercase, and this helps us reduce the dimensionality. So what we can do is we take, even if there's an uppercase letter here, we're actually going to be lowercasing it and doing those things like that. So that way we can match it to our alphabet. And this is a way just to speed things up, and some of the data can be thrown away. However, you might want capital letters. And if that's the case, you can update your alphabet to also have capital letters. Here's a few more hyperparameters. We've got our input dimension, output dimension, learning rate, and epsilon. Since matrices are generally fixed when you've defined a model, we need to be able to have an input. There's got to be an input layer for the model, and it's a fixed size. And so in order to do that, we have to create a shape that matrice can be used to then multiply as we transpose our input data and multiply it against that matrice. The matrix. So I just found the longest sentence in our case, and I gave it the length of 72. Output dimensions, we only have one output, and it's going to be a floating point number, and it's going to be optimized towards whether it's got a negative aspect in the sentence or not a negative aspect in the sentence. So it's a really simple model. We can go further and say we have more outputs, and we can say it's got 5 output dimensions, which then allows us to classify other things in the model, but we have to teach the model what those things are. Oh, maybe it's got like nouns, a noun, for example, like it's got a person, place, or thing, and it's embedded, and you want to be able to teach the AI that a noun is present or a noun is not present. And so you'd be able to teach the AI that by giving it an extra output, and then you would label that sentence if it has that or not, and so the AI would be able to understand that in that case. But for now, we just have one dimension. The learning rate describes how fast we're going to backpropagate our optimization. Once what happens is during training time, we'll take one of the sentences, for example, the sentence here. We'll vectorize that sentence and then put it in the right dimensions, and then we'll run it through the model once, because the model's we already built the model in this case. We've got a bunch of matrices. We're going to run that through the model, and it's going to give us an answer. It's going to be wrong, probably. I mean, it could be right, but it's going to be wrong. And then what we do with backpropagation is see what the delta is, how far off it was wrong. So like it could be off by like 1,000 or 2,000 or some big number or some very small number. And then we multiply the learning rate against that delta. And then we just ever so slightly modify all of the floating point numbers in the matrix. So this is a hyperparameter, the learning rate, and you can increase it or decrease it. The more you decrease it, the longer it will take to train the AI, because you're making smaller increments. If you increase it really big, then the AI could learn very quickly. However, it will overgeneralize or undergeneralize. It won't. There's a balance here, and it's possible that it can get stuck if the learning rate. So there's like a really good point. You can also change the learning rate through different epochs. Epsilon is another hyperparameter that I've defined here that describes what is the lowest possible value that is going to be present when I'm importing data through the embedding approach that I'm using. Like when I'm vectorizing a sentence and turning that sentence into a bunch of floating point numbers, I want to make sure that I don't have any zeros, because zeros will be deactivating neurons as it passes through the matrix. You might want in some cases. However, because some of my sentences are small, I'm going to be, as you can see here, there's a bunch of empty space in some of these sentences. I don't want all these to be zero. I want to be able to still leverage those. And so I've defined an epsilon, which is going to be a low number, so that way I still get some activation or at least some throughput, but it doesn't block things altogether. When we're building a machine learning model, we have to prepare the data. We have to make sure the data is clean. We have to look at it. We have to sanitize it. We have to make sure that, because this is what the computer is going to use to train itself, right? It needs to have good reference material, you don't want to just throw out any random stuff. You want to give it good, clean data. And so we've got our data here. We've got a bunch of sentences, for example, and each sentence is very general. Like you might have a hard time figuring out really what we're trying to teach the AI in this case, but it's really simple. We just want to see whether there is a negative aspect, see like if there's a negative aspect or not in this case. And then we'll be able to train an AI to sort of detect the tone of a sentence in this case. And we need to make sure this data is clean because the AI is going to see what we've trained it to do, and it's going to repeat what you've trained it to do. So we got to make sure it looks good. So this data has already been cleaned and verified, but the next thing we need to do is prepare it for the import, right? We got to make sure the data looks good. So what we're going to do here is we're going to parse this training table line by line. We're going to ignore the header, right? So this is the header section, and we don't need the last line here because it's empty. And then we're going to separate that into features and labels. And a feature is just input data. In our case, this is the sentence. So we're going to prepare that data. So for every sentence, what we're going to do here is we're looking for the delimiter, which is a pipe symbol. We're going to remove any trailing spaces, and then we're going to lowercase the entire sentence because our alphabet that we're training this on is all lowercase. Now we could add more, we could increase that if we wanted. Actually, we could do that right now, right? So we're going to do this, and then we are going to have lowercase and uppercase. And then we could remove the dot lower. There we go, it's removed. I'm pretty sure that'll work. We'll find out. And so now we've defined more tokens, about 26 more tokens here. It'll be able to leverage when it's training. So it's going to give it more dimensionality. I mean, not by a lot because there's not very many uppercase characters here. It looks like only the start of the sentences. So, meh. The training labels are the output data. This is the target. This is what we want the AI to find as the answer. It's going to optimize towards this answer. It's like, here's the input sentence, here the features, the input sentence, the output targets are the labels, and in that case, so you can see here, this is the output. There's the negative part, negative aspect. Just like, hey, if you detect something in the sentence that isn't super positive, then we can label it approximately negative aspect. And we did it. We prepared our data. We've made it straightforward, right? The features, right here, are our sentences. The labels are the output data, and I had a 1 or a 0 as like slightly or as a negative aspect of the sentence or not a negative aspect of the sentence. And we are delimiting by the pipe bar, and we're getting that number and we're converting it to an integer and then putting it into an array so that way it matches up. Our features and our labels are matched up now. The data is ready to input into an AI model. After you've prepared your training data for the machine learning model to build AI, you can do the next step. We've got all of our sentence data, we've got our answers. So here's our training data. We've got sentences and our answers. And we want to optimize a model to be able to generally define, find whether a sentence has a negative aspect to it. So we'll be able to train the model on these things here. So all of our data is loaded in the training features and labels. Next, we need to create our embedding, which will vectorize the data. It'll tokenize, and then it will embed that data into a vector. So basically what we need to do is we're going to take a sentence that looks like this, right? This sentence here, and we're going to turn it into a matrix. And a little matrix looks like this. And what we want to do is during this conversion process is we want to be able to give the computer some context or understanding of what that sentence looks like. Because the computer doesn't have eyes, but we can give it some sight, essentially. And this is a gradient, a nice, pretty smooth-ish gradient. We could do better, but this is a just nice getting started example. We want it to be able to see the differences based on position of the characters. It'll be able to identify different words, the spaces. So we'll give it as much vision as we possibly can. So there's a lot of ways to turn those sentences into matrices or inputs, vectors, through embeddings and all sorts of all those fun words, lots of fun words there. So first we need to tokenize the sentence, and here we go. We need to generate a token map, and the token map is simply, so we got our alphabet here, which is going to be 26 capital letters, 26 lowercase letters, and then we've got our numbers, and we got a couple of symbols. We got a space, an exclamation point, and a single quote tick. Alphabet, and then we're going to generate a token map by creating a Python dictionary, defining the range of the vector between each of the characters, and then we're going to iterate and increment a range across all those characters to assign a floating point number. So we'll print that out here really quick. Just so we can see what that looks like. And so we've got like capital A starts with -2, then it goes is a little bit further and a little bit further, a little bit further for every letter until it gets to the last symbol, and that is 1.93 number. So it's really simply creating like a nice smooth array based on all of our alphabet letters, starting with -2 and ending with +2. So simply, in order to then translate our sentence, we just take that token map and then output the integer or the floating point numbers, in that case, for every single letter in our sentence. So like this sentence here, we would see T would correspond to, well, it's capital T in this case, right? Here we go. Capital T will be -0.83. And then we'll just keep appending into an array every single letter based on its token. And then we tokenized our sentence. But it goes a step further. Well, you could stop here, actually. You could stop here. You don't need to go any further. You don't need to do an embedding. You don't need to define extra things for the AI to look at. However, I wanted to do that anyway. And you can do that by generating a vector with an embedding that does self-correlation. So this second method here is optional. You don't need to do it, but I wanted to because I thought it was fun. The most important thing is you need to take the token map, your sentence, and then iterate through every letter, and then assign the index to generate a vector. That's it. That's right. That's it. So at the end of it, you'll have a sentence that'll be translated to something that looks like this. So here's a bunch of letters. That sentence will be translated into a vector that is uniformly sized. And that uniform size is necessary because our AI models are all fixed size matrices. And if you've been using anything like ChatGPT, you'll probably see things like input limits, right? The input length, the maximum input, and the maximum output. That's all because they're generally fixed sizes. So you only can put so much detail in. If you're learning about how AI and machine learning works and getting your hands on with some Python code, here's a quick example that I really like to refer to when I'm building any sort of AI model. I like to sort of reference off of this pattern. I mean, they're all kind of they're the same patterns overall, but this is something I like to keep it simple from getting started. So we already have our training data prepared, right? It's all vectorized. Our training data is the sentences, which are our features, the input data, and then our targets are all defined. So we've got our X and Y, which are our features and labels. We're ready to go. So we want to define the model. And the model, a common model, is a sequential model that we see, and this is what that looks like. So we're using Keras, which is the high-level abstraction on top of TensorFlow, but you could also use PyTorch. Sequential, which will define our ability to add a whole bunch of layers into the model. So we have several hyperparameters here that are present. We've got our hidden dimensions. So based on the size of the model, we want to give it some extra oomph by giving it a number of units, right? These are called units, the hidden. How big is that matrix going to be? So we've got our matrix with our input dimensions, which are going to be 72. In this case, it's 72. That's just the limit of this is what that matrix looks like, the input matrix. So whatever data you're feeding into the model must be shaped in that form. It must have that number of dimensions. And a dense layer is just a regular matrix. And then you can say how many units or how many floating point values are in that. These are the parameters or the weights. So we have several dense layers here. We've got 3 dense layers. They're all roughly the same size, except the last one and the first one. The first one is going to be shaped specifically based on the input dimensions by the number of hidden units, which I've defined here. So that's going to be 720. So this will be 72 by 720 units, which is a lot of units. So our input matrix will be 10 times 72, it'll be 720 parameters for this first layer. And the second layer is going to be 720 times 720, which will be half a million parameters. It seems like a lot. That's a lot of floating point. We probably don't need a model this big for what we're going after, at least with this small amount of training data. As you get larger amount of training data, you want more parameters so it can have a better picture and better memory based on the input data. But that is a hyperparameter, right? We need to see how big this model is going to be and how much it needs to know and remember. And if we go too big, you have a chance of overfitting. If you go too small, then it overgeneralizes. And then our final layer here is 720 times 1, which is our output dimension. So we're just going to have the final layer at 720. So we've got like a middle heavyweight parameter here in this case, model that is going to be where most, I guess, of the memory and other things happen. You can shrink this and grow this and play around and have big ones and small ones, and just that's how you do the model, and you get to play around with it. because you just add these as much as you want. Let's just add a whole bunch of them. And if you think about the LLMs these days, what was it, GPT-4 has something like 90 layers, more or less, which is a lot. But this is where the deep learning comes from, is just multiple layers. After each input layer, we have an activation, which will, as matrices are being multiplied, we get the input data, which looks like this. And this matrix is going to be multiplied, transposed, and multiplied by the input matrix from the model. And then that's going to give an output, and that output is then transposed and multiplied onto the next matrix, and then the next matrix, which is the output model. And what we want to do is make sure that nothing explodes, right? Because it's possible that as we're training, the model can increase those numbers to really big numbers, right? 1,000, 10,000, a million, a trillion, and then you run out of memory. So we don't want that, and we don't want any of those nodes to explode and cause the model to fail. So we add an activation onto it that sort of creates a nice bounding box where it still has a little bit of information if it tries to go really high or really low in the value. So we want to keep as much information as possible, but we don't want to explode the model and have it fail. So that's what an activation is for each layer. And for our output, since we're just training it on detecting one thing, whether the sentence has a negative aspect to it, we only have one dimension output. And then we're using sigmoid with binary cross entropy, which will help us optimize towards that answer because it's just one output, one category. And we're using sigmoid here as the activation because sigmoid gives you a value between 0 to 1. Tangent gives you as value -1 to +1. So it kind of gives you like a range because our input model has negative numbers in it as well. And other reasons, it gives you, I tend to get better results by having 10H. Now there's also these ReLUs that you can use, and I tend to see that you need even more parameters often. However, that will end up being more efficient because it's a faster, what do you call it? ReLU is more simple to calculate because there's no, this ReLU is faster than 10H. Yeah, that's how we do. So you can play around with these activations to see if you get different results. These are the tuning parameters, right? So depending on your input data and your output target. So the last detail here is the model. We're compiling it with the optimizer and our loss function. You can use a variety of loss functions here, like mean squared error, like a cross categorical entropy, which allows you to find multiple. So if our output dimensions has multiple categories, you'll change that to, it might be a much bigger number. So like 300, for example, you might have 300 outputs. This will be a softmax, and then you'll say categorical cross entropy. But in our case, we just have a single output, so we just need sigmoid and a binary cross entropy here. We're using our standard gradient descent optimizer, takes all of our input data, randomizes it, and shuffles it, and then it feeds it through the feed-forward neural network, and then it will apply back propagation based on the loss function, and then apply iterative adjustments to all the matrices based on our learning rate. And it's really that simple. So this is our model. And I love it because it's just, about 20 lines of code here that defines our model, and you can get more complex. You can add other things. There's different kinds of layers. There's a lot of things we can do here. Let's train the computer. We can train the computer to do our bidding, anything we want it to do. We just have to give it, we have to train it first. We have to say, if you see this, I want you to tell me about this or do this thing over here. What's cool about that is you can give it just a whole bunch of examples to learn from, and then it can generalize a pattern to then going forward in the future, if it sees something new, it will get pretty close or as good as possible, even better than a human. It'll be able to learn and use that knowledge in the future. So we've already created our model. We've got our input data, which are sentences here, and we want to detect whether there's any negative aspect to those sentences. And so we want to train the model. So we created our model here. Our model is a simple sequential model, which has some layers in it. Here, very basic, very standard, a nice, common, good, foundational example. And then we run the fit function, which is the train function. Since we're using Keras here, they give us a lot of nice high-level APIs that make it a lot more simple when we're training our model. So we've got our .fit, we've got our features, which is the X. These are the input data, which are our sentences. The labels, which is Y, which are basically our targets. This is what we want you to learn. If you see this, this is the answer. If you see this, this is the answer. And so you're giving the AI that detail. We're saying that we're going to give it 4 sentences at a time, so that way when it's calculating the loss, how far off it was from its answer, we'll be able to bucket several input pieces, like 4 sentences in this case, and then create a delta of how far off it was in its answer. So as we're training it and we're like, hey, here's the input data, give me your answer. It will give you a wrong answer, and we say, okay, correct yourself by how far you were off, how incorrect you were, and base it on our learning rate. So we say, okay, you were off by this much, adjust based on that delta. It looks like about 0.1% based on its loss. So if it was off by 100, then we're just going to adjust the weight by 1/10 of a percent in that case. And so this is it right here. This is where it's like computer train. Epochs describes how many times it's going to go through the complete data set. Since we're iteratively training the AI and just ever so slightly adjusting the matrices by the learning rate, we want to repeat the data a few times, in this case 500 times, to get that, so that way it gets a better. You can have it go through once, but it won't learn enough. You need to sort of slowly repeat over time because we're adjusting these weights in the matrices. Let's do it. Let's see what that looks like. Okay. All right. So we executed it. So what's happening here now, it's running through all the examples. It's learning, and that's giving you the loss function, which defines how far off it is from its, from how far off it was from the actual answer, right? So the loss function will continuously provide a lower and lower value, which then allows us to see that it's actually learning something. Like okay, this is a good validation of you're actually moving forward with the model. The model is working. But now there's a whole bunch of other things to optimize, like generalization. Overfitting is a problem, right? It's possible that this number can get approaching 0. Could work depending on your use case, but it also means overfitting. So guess what? We've trained the model. It has 100. My math function. The accuracy is 100%, well, a little bit higher than 100%. So here's, what do we do here? So I output it. I want to test the model. So I give it all of the sentences that I've trained it for. So we've already trained it. And then we're going to say, okay, here are all the sentences again. Tell me what the answers are. And then I measure how far off it was in its accuracy. And then I print its answers based on here's the real answers right here. The real answers versus what it gave me, what it thinks the answers are. And it got every sentence correct. So like this point here is 0, this is 0. The second one, the last of the second, there's 1 is 1. So it got every sentence right, which is great. Now I have myself a little text input, so I can, here for example, there's one of the sentences I trained it on. It's my class was helpful during the group assignment. And it says there are no negative aspects found in this sentence. It did it! It worked. Now I've only trained it on a few sentences, so there's not a whole lot it could generalize on. So like maybe if I type a whole bunch of gibberish, it's still going to give me an answer, and it says that gibberish has a negative aspect to it, which I guess you can kind of infer. General good experience and happy about the class. Let's see what happens. It says it thinks that's negative, because what we need to do next is we need to train it on more data, because that's a sentence it's never seen, and the more sentences we give it, the better it can generalize going forward. So what we can do here is we can say, so for example, if I have good, it thinks that's negative, right? So we can go back to our training data real quick and then add a new sentence, good, like that. Retrain the model, and it'll be looking for this. It knows that it is not a negative aspect. Okay, so I've retrained the model here with that new data input. So I've added it a new input here. So I should be able to say good, and it should give me a low negative aspect score, and it does. It actually gives a really low score. So I was able to teach it something new. And so the more training data you give it, the better it can generalize, and the better your model will perform. And that's why data is really important when it comes to AI, because we need a lot of data to be able to give the best possible answers. And that's it. We did it. We created an AI. We made it work. It's going to do work for us now. And so now that we have this model, we can just basically train it to do whatever we want, and it can do that work going forward forever. And that's why it's so powerful and so cool. It's mostly tireless. And if we wanted to make this economical and energy efficient, we could power it by the sun, because there's so much solar energy coming at us these days. We could easily power our AI on sustainable energy, and it can do whatever tasks we need it.